All right, so we're just going to keep going with some more examples of u substitution because I want to show you that it works with more than just trig. Okay, so let's take a look at a third example. All right, so let's look at 3x squared times 5 plus x to the third, and that's all raised to the 7th dx. Okay, so again, kind of ask yourself, because we're basically trying to reverse the chain rule, all right? Is there a part to this integral that looks like it could be the derivative of another part, okay? And so 3x squared kind of looks like, or it is the derivative of x cubed, all right? But we can't separate the 5 plus x cubed. So I'm going to say u equals 5 plus x cubed. And I don't want to use the 7. I don't want to raise that to the 7th because when I take the derivative of it, I'd have to use the chain rule, and then I'd have way more than I need, okay? So I'm not going to put the 7th on this. That'll come later. All right, so I'm going to take the derivative, and remember, I'm just going to hold the dx for the end of the derivative. So the derivative of 5 is 0, and the derivative of x cubed is 3x squared, and then I'm going to tack on the dx there. Okay, so it looks like I do in fact, oh, I wrote this wrong. That's okay. I do in fact have du, all right? Du is the 3x squared times the dx, all right? And remember, this piece is the u, so I still have to use the 7. So when I rewrite it, I have u to the 7th. The 7 is still part of my problem, and then everything else turns into du, okay? And now I have a power rule. I can literally just apply a power rule, right? And so I'm going to add a power and divide by the new power and add c. But I'm not done until I actually plug what the function of x back in. All right, now I don't usually like to leave it like over 8, so I'm going to do 1/8, and then I'm going to plug in 5 plus x cubed and raise that to the 8th plus c, and then I'm done, because if it starts with x's, it has to end with x's. Okay, now yeah, that's good. All right, let's do another one. All right, what if I had the integral of 12x cubed dx? Okay, 12x cubed, 12x all cubed dx. All right, so this is not like a problem where I could factor the 12 to the front, because the 12 is cubed. Now I guess I could actually cube the 12 and then factor it to the front, but I want to make it even easier on myself. Okay, and so essentially, if you have more than just x raised to a power, that's a good indicator that that's your u. Okay, so the stuff that's more than just x raised to a power. All right, so 12x is probably my u. Sometimes it's a guess and check type thing. So du is going to be 12 dx. All right, so I've got the dx, and remember, I can compensate for a missing coefficient. Okay, so I can compensate for the 12 by just multiplying, I can multiply by 12 as long as I multiply by 1 over 12 as well. But I don't really need the 1 over 12 inside the integral, so I'm going to put the 1 over 12 in front of the integral. And so I'm still technically multiplying this whole thing by 1. I'm just kind of putting them in a place that's more user-friendly. Okay, so this 1 over 12 stays, 12x is my u, and the cube stays, and dx times 12 is my du. Okay, so I'm literally substituting u's and du's in place of x's. That's how it got its name. All right, then I can actually integrate with a rule I already know. the power rule. All right, so when there's a constant in front, that's going to stay in front. Then we apply the power rule, so we add a power, divide by the new power. Don't forget your plus C. All right, and then when I go to plug, and you can either write it under it or off to the side, but when I go to plug the U back in, all right, I'm going to go ahead and combine my fractions and put that in front of all of that. Okay, now of course if you had a calculator you may want to actually figure out what 12 to the 4th is and divide that by 48, but I'm not worried about that. Okay, I'm just worried about you practicing applying the rules. All right, so I just have lots and lots of examples for us. All right, number 5 here. All right, I'm going to do the integral tangent to the 5th of x times secant squared of x dx. Okay, now when you have two trig functions in there, especially when like the powers are way different, okay, you really kind of you need to ask yourself, is one trig function the derivative of the other? Okay, all right, so that means it's important that you know your trig derivatives. All right, and I happen to know that secant squared of x is the derivative of tangent of x. So notice I did not say tangent to the 5th. I just said tangent of x. All right, so I'm going to hang tight with me. All right, so I know that the derivative of tangent of x is secant squared of x. I'm going to go ahead and multiply by my dx to get it set up right. All right, and so I actually already have that. All of this is du, and tangent of x is u, but it has a 5th power. So what I really end up integrating is u to the 5th du. Okay, and so that's what I'm going to apply the power rule to. And I'm going to add c, and then I'm going to go back and I'm going to plug in u, which was tangent of x, but I'm going to put the 6th in the middle because that's one way to write, right? Tangent to the 5th of x is the same thing as tangent of x all to the 5th. All right, so that's what I'm doing here. Okay. All right, let me give you another one. It's going to look very similar. All right. All right, I want to integrate secant to the 8th of x times tangent of x dx. Okay. All right, so again, we've got two trig functions. We need to think to ourselves, is one the derivative of the other? All right, but tangent and secant can kind of go both ways, right? So then I'm like, well, which one do I pick? Well, you can either guess and check, or, all right, because you've got this bigger power, this secant to the 8th of x, all right, it's more than likely that whatever is raised to that bigger power is your u. Okay, so secant of x is probably your u. All right, let's see if we can manipulate this so that we can make, we can set it up with perhaps a power rule. All right, so the derivative of secant x, you need to remember, is secant x times tangent x dx. Okay, so when I set up the du, when I figure out what part of this is du, I'm going to need to use one of these secants and the tangent and the dx. Okay, so one of those secants, all right, and maybe you want to see it written out. One of those secants times tangent times dx, all of that is du. Okay, so what does that leave for the rest? All right, well, if I used one of the secants, then I technically only have secant to the 7th left. All right, and so when I change this into u substitution, secant of x is my u, and that's raised to the 7th. And everything else is du. And that's a lot less complicated to work with than trig functions. Okay, so we add a power, we divide by the new power, and we add c. And then last but not least, you do need to go back and plug u back in. All right, so again, let's remember what it was. It was secant of x. And again, you can write it as secant of x, all raised to the 8th like that. Or you can put the 8 in the middle of the function like that. All right. Well, let's just keep on moving. How many I got there? Okay, that's enough for one page. Let's move on to another page. All right, example number 7. All right, let's look at one with a radical. All right, so I've got x to the 3rd times the square root of x to the 4th plus 5. And with u substitution, almost always, in fact, I have a hard time thinking of times when it's not true, if there's a radical in the problem and more than just x underneath, what is underneath is almost always the u, all right? Not the radical, but what's under the radical, okay? Because again, if you kept the radical and then you took the derivative of that whole thing, you'd have to bring the 1/2 to the front, you'd have to keep what's underneath and subtract a power, and you'd have to multiply by the derivative of what's inside. And so you would have to have all of that extra stuff for du. And we don't have all of that extra stuff, okay? And so that's why it's important to make sure that you don't take too much for your u, all right? So don't use the radical. All right, so since I don't have the radical here, du is a lot easier. I just get 4x cubed and of course dx. All right, so what ends up with, what happens to the radical, right, is what's underneath it is u. So I'm really taking the square root of u, which I'm going to be able to rewrite as u to the 1/2, okay? But I don't actually have du yet, right? I have part of it, I have x cubed times dx, but I still need a 4, right? So remember, you can multiply in anything you want as long as you balance it with the reciprocal. Excuse me, let me go back. You can multiply any coefficient that you want. Right? You can't multiply by x's. But you can multiply any coefficient that you want as long as you balance it with the reciprocal, all right? And again, we don't need the reciprocal inside the integral, so I put it in front. Right, now 4x cubed times dx is du. So I have everything I need and I have the extra 1/4 in the front. And now I'm ready to integrate. So I keep the 1/4, I add a power, divide by the new power, which is the same thing as multiplying by the reciprocal, and then add c. And then all I need to do now is to simplify my fractions and plug u back in. And again, you can always go back and check yourself by taking the derivative. All right, you can always go back and check yourself by taking the derivative. All right, now what about some of the other functions that we've learned? All right, so let's look at an e. All right, e to the 2x dx. All right, well, typically e to the x is its own derivative and its own integral. All right, but let me show you. If I say that, okay, and the reason I need u substitution is because it's e raised to more than just x, okay? Now, if I take the entire function, e to the 2x, then the derivative is another e to the 2x times a 2. And I don't have e to the 2x in two different spots, okay? So I can't use e as part of my u function, okay? But I can use what it's raised to, okay? And then that derivative, even though I don't have it, it's a coefficient times dx. So I can compensate for that one, right? So I can multiply in a 2 as long as I balance with the reciprocal in front. And then when I rewrite this, what am I actually integrating? Well, I didn't do anything with the e. I just said 2x was the u, and everything else is the du. And that's one of the rules that we wrote down when we first listed all the rules, right? The integral of e to the u du, once you have it in that form, the answer is e to the u plus c. Okay, so we've set it up in that form. We find there it is. All right, and so then the 1/2 is going to stay, and the answer is e to the u. And then, of course, you need your plus c. And then before you finish, you need to plug u, which was 2x, back in. All right, and then you're done with that one, okay? All right, let me give you another one with an exponential function. All right, how about the integral of 2x times e to the x squared dx? All right, so we have an exponential function, and again, you're going to learn this, but most of the time when you have an exponential function, whatever it's raised to ends up being your u, okay? You should probably check that first. All right, if I take the derivative of x squared, I get 2x dx, which I already have both of those pieces. All right, shoot, I did it wrong again. All right, I'm changing this one. I did not mean to have the 2 here already, okay? What I wanted to do was to show you that you have the x and the dx, that's good because you can't compensate for those, but you still need a 2. So I can multiply that 2 in as long as I balance it with the reciprocal, okay? And then I can rewrite it, and I'm really just integrating e to the u du. So the 1/2 stays. The answer is e to the u plus c. And then last but not least, always make sure you go back and plug u back in. Okay? All right, now let me give you another one that has e in it that is different. All right, what if I give you something like this? E to the 3x over 1 minus 2 e to the 3x squared. Whoa, right? Lots more going on. All right, so I have more than one e to the x, and I have a binomial raised to a power, right? And so a binomial raised to a power is definitely more complicated than a single e, right? So when you're trying to figure out what's u and what's du, start with the more complicated piece for your u, all right? So I'm going to take this binomial. Now, I don't want to keep it squared because then I would have to apply the power chain rule, and I don't want to have to do that because I really don't have a lot of extra stuff going on, all right? So I'm not going to carry the square with it, and I'm going to take the derivative. The derivative of 1 disappears. The derivative of negative 2 e to the 3x is negative 2 e to the 3x times 3. I do need the chain rule there, and I need my dx. All right, so du ends up being negative 6 e to the 3x dx. All right, so right now, everything that I chose for u is on the bottom, and it is squared. Okay, well, what can you do with a u or something on the bottom that's raised to a power? You can bring it to the top and make the power negative. All right, and then I have e to the 3x times dx. All right, doesn't matter that they're not right beside each other, but I am missing that negative 6. So I do need to multiply in a negative 6. That's why I'm using parentheses. I don't want it to look like minus 6. All right, but I also have to multiply by the reciprocal of that in front, which is going to stay. and then e to the 3x times negative 6 times dx is du. Okay, and now it's not an e problem at all. It's not an exponential integral at all. It's a power rule. All right, so how does the power rule work? Add a power, divide by the new power, which is the same thing in this case as multiplying by -1, and then add c, and last but not least, put it all together. We get positive 1/6. U moves back to the bottom so that it has a positive exponent of 1, and then we have our plus c. All right, how many more do I want to do before? All right, I just want to do a couple more before I stop this video. All right, let's just slide over here. And as I can fit them here, I think. Okay, so let's look at the integral of dx over 2x minus 1. All right, so that's a little bit different. All right, well, you do need to keep in mind that that is the same thing as 1 over 2x minus 1 times dx. All right, so maybe that kind of jumps out at you. All right, or perhaps you want to think of it as 2x minus 1 to the -1 times dx. All right, maybe you see the issue, or the type of problem that this could be by looking at it in this form. All right, so 2x minus 1 is on the bottom. I can't separate it. All right, I can't say one little piece of it is u because of the addition or subtraction. All right, so I am going to say the whole bottom, or if I'm looking at it in this terms, everything that's raised to a power, the 2x minus 1 is going to be my u, and then du would be 2 dx. Well, I've got the dx. Remember, I can compensate for a coefficient as long as I balance it with the reciprocal. Right? And so then when I rewrite this, I really just have 1/2 times u to the -1 du that I need to integrate. Sorry. Leave room for the integral symbol because I haven't actually integrated yet. That's important. All right, haven't actually integrated yet. All right, so then how do you integrate u to the -1 du? All right, well, hopefully you remember that that is the natural log of the absolute value of u. It is important that you remember those absolute values. All right, plus c, and then you finish by plugging in u. And we're done. And you have to leave the absolute values around it when it's still a function of x. The only time you can drop the absolute values is if you already know the function is always positive, like x squared is always positive, or you're plugging in a number, okay? All right, just a few more. All right, number 12 here. All right, let's go back to a little bit of trig. All right. All right, so I've got trig functions on the top and the bottom, and technically the individual trig functions are derivatives of each other with or without a negative, right? But one of them is part of a binomial, right? So you really should consider that to be your u, okay? The other thing you need to know is that you can never be on the bottom, okay? U will never be, well, okay, that's not what I meant. Okay, u can be on the bottom because you can bring it up to the top, but du will never be on the bottom. Du will never be on the bottom. So when you have to choose between the top and the bottom actually should be your u because du cannot be on the bottom. All right, so let's take the derivative of 1 plus sine of x. All right, so the derivative of 1 is 0. Derivative of sine of x is cosine of x. Go ahead and put your dx on the right, which we already have, right? So let's think about what we have. We have du on top and u on the bottom, right? But we know that that's the same thing as u to the negative 1 du. And then we know that's one of our special, right? We can't apply the power rule because that would make us divide by 0. So then that must be the special one that gives me the natural log of the absolute value of u plus c. And to finish, we need to plug u back in. And we're done. All right, and then the last one for this particular video. All right, let's look at 13. Right. Whoa, what if there's a natural log of x in the integral? All right, well, I didn't give you a rule for that. All right, that's because that's not something we're going to cover in this class. All right, so ln of x must not be what we're integrating. All right, so if we don't know the integral of it, it's probably our u, because we do know the derivative of it. All right, what's the derivative of ln of x? 1 over x, and we're going to go ahead and bring the dx over. And if you think about this, an x on the bottom is the same thing as a 1 over x times the top, right, times dx. So I actually do have everything that I need. All right, so let's kind of put it all back together and figure out what I'm integrating. So 1 over x times dx is my du. ln of x is my u. So all I'm really integrating is u du. And then how do I do that? I apply a power rule. I add a power, divide by the new power, and add c, and then make it look nicer. Put a fraction in front, plug u, the function, back in, and keep the square, and add c. Okay? All right, so I do have a lot more examples. Where's my mouse? Okay, but we're going to stop this video here. Whew, that's way longer than I thought it would be. Okay.